All right, it's my pleasure to welcome everyone to the Oxford-Bristol Set Theory Seminar. And it's my special pleasure to introduce today's speaker, Kameryn Williams. He was a student of mine in New York. He got his PhD at the Graduate Center of the City University of New York in 2018, and then went on to his current position at the University of Hawaii. And he's going to be speaking on the geology of inner mantles. So Kameryn, please go ahead.
Yeah, thanks, Jill. Thanks for the invitation to speak here, and thanks to everyone who showed up. So I should say also part of this is joint work with Jonas Reitz. I don't think he's able to make it to today's talk, but he's definitely is behind a lot of the ideas. Okay, so I'm breaking it up into like an introduction, then I have positive results about the inner mantles and negative results about the inner mantles. Okay. And so when I said that Jonas is
Kameryn,
kind of...
Could you maximize your display?
Oh, I'm so sorry. I forgot to do that.
It works a little better that way.
I'm sorry. So when I said Jonas is behind a lot of this, this whole sort of subject in set theory of geology begins with a question he asked, which is, what if you did forcing but backward? Okay, and so, rather than thinking of V as the ground model and then going to an outer model by forcing, we want to think of V as the forcing extension. We have some inner model that we got to as the ground model. So definition then, a ground is an inner model, say W, so that V is a set forcing extension of W. You could talk about like class forcing grounds, but that ends up being kind of more difficult to formalize. So we're going to focus on set forcing grounds. Okay. So kind of the basic definition of set theory of geology then. And you can, prove a lot of facts about grounds. So here's kind of two fundamental theorems about grounds. So the first one, due independently to Laver and Wooden, I think building upon work by Joel, is that the grounds are uniformly first order definable. So you can talk about these things in ZFC. The second fundamental theorem is due to Toshimichi Usuba. And so he proved this strong downward directed grounds hypothesis. So what does this say? This says that if you take a set-sized collection of grounds indexed by some set I, then you can find a ground beneath all of them. So if you have a whole, set many, there's one below all of them. And okay, you might say, why is this interesting? And I'm not going to go into this talk, but basically a lot of the nice properties we get follow from Usuba's theorem. So for example, Usuba's theorem will imply the mantle we'll look at later satisfies the axiom of choice, which was not known before his result. Okay. So maybe an aside, since both of those I said you need a choice to prove. It's an open question whether this grounds definability theorem holds without the axiom of choice, but there is partial results known. So Gitman and Johnstone showed that if you satisfy a large enough fragment of DC based upon how big your poset is, then it's going to be definable. So they basically just like refined the Laver-Wooden result to get exactly how much choice was needed. Then separately, Usuba showed that if you have a proper class of what he calls Lowenheim-Skolem cardinals, then you do get this uniform definability of the grounds. And so these are just basically cardinals that let you do the Lowenheim-Skolem theorem. Of course, in ZFC, every infinite regular cardinal, maybe all infinite cardinals are Lowenheim-Skolem cardinals. And also, if you have these, you can talk about symmetric grounds. If you do like a symmetric extension, but backwards, that makes sense in this context as well. Okay, but I'm not talking about choiceless geology. Everything in this talk will be about choice. Okay. So the, kind of to build towards what's in the title, the inner mantles, is let's talk about the mantle. So what's the mantle is we're going to intersect all the grounds. The grounds are uniformly definable, so we can define the mantle. You just say something's in the mantle if it's in every ground. And the inner mantle, it turns out, is an inner model of ZFC, so including the full axiom of choice. As I said earlier, Usuba's theorem about the strong downward directed grounds hypothesis is used to get this result. And indeed, it's the largest set forcing invariant inner mantle. So if you take V, you do set forcing, you can't change the mantle, and it's the largest inner model of this property. Okay. So maybe let's see some simple examples of what the mantle is. So maybe the simplest example to start would be if you look at L itself. What's the mantle in L? It's L. Okay, that's pretty trivial. If you do non-trivial set forcing over L to get, say, L of G, then the mantle is going to stay L. Of course, as we said, it's not changing by set forcing. So it's, clearly going to be the intersection of all the grounds in this case. On the other hand, if you do a class product of co-enforcings, then you're still going to be able to get that the mantle itself is L, because you could just look at like tails of this. If you added all but set many of the Cohen sets, then that's a ground. And so you intersect all of these, you're intersecting these shorter and shorter tails, you're going to get left with just L. And so this is the case where you have that the mantle is not one of the grounds. So it's possible to then have lots of grounds, but the mantle not be among them. On the other hand, and this is, I don't want to say all of Usuba's theorems are fantastic, but they are, is if you have an extendable cardinal, then the mantle must always be a ground of V. So given sufficient large cardinals, you have a smallest ground. And I think recently it's been shown that a proper class of supercompacts is not good enough to get this, that you can force like the mantle to not be a ground from a proper class of supercompacts. So this is pretty close to an optimal result. Okay, so a simple example showed that the mantle can be all of the universe, it can be very far from the universe, but can we make some general statement about what the mantle can be? And yes, we can, and by we, I mean Fuchs, Hamkins, and Reitz did this. So they gave two class forcing notions. So one of them forces the ground model to be the mantle of the extension, and the other forcing notion forces the extension to be its own mantle. So you can kind of think about this in comparison to HOD. You can force the extension to be HOD, to be its own HOD, and you can force the extension's HOD to be your ground model by class forcing. Okay. Note, of course, this has to be a class forcing notion. If it was set forcing, we couldn't change the mantle at all. And as a corollary of this result, or really just the first part of it, the theory of the mantle is ZFC itself. Since any model of ZFC has a countable elementary submodel, and that countable model is the mantle of some larger model, then the only thing ZFC proves about the mantle is that the mantle satisfies ZFC. And again, you should think about this as being similar to the analogous result about HOD. What's the theory of HOD? ZFC. Okay. So we can kind of make the mantle kind of whatever we like is the idea here. And so I want to talk about how to prove these two results, because especially the forcing the ground model to be the mantle of the extension is going to be built upon for later work. Okay, so kind of the fundamental lemma here, if you want to prove anything about the mantle, is if you have a ground, then the ground has to agree with V with the tail of the continuum pattern. If you're just doing set forcing, you can't affect the continuum pattern on a cofinal set of cardinals. So I think we all know this lemma. And so because of this, if we do want to force V to be the mantle in the extension, then we just have to code every set of ordinals cofinally often into the continuum pattern. Because then, if you're in a ground, you can reconstruct that set of ordinals by looking at the continuum pattern on some far enough tail. And since every set can be coded by a set of ordinals, that's going to give us every set is in the mantle. Okay, so there's a really slick way to do this forcing, which is just do an ord length iteration of lottery sums. And so at each stage, you're going to generically make GCH hold at alpha or fail at alpha. So in a bit more detail, let's pick out an appropriately spaced out coding region. If we start with GCH in the ground model, this can just be, say, all the regular uncountable cardinals. If GCH fails, we'll have to look at strong limit cardinals to kind of pick out where it is. So if we are changing around where GCH holds and fails, we aren't destroying the coding region, but it's not too difficult to work out what you need to do. We're going to do a set support iteration, and at stage alpha, we do this lottery sum, which generically either makes GCH hold there or fail there. And then a pretty easy density argument shows that we get every set of ordinals is then coded in cofinally often in the continuum pattern, which implies they're in every ground, which implies that every set is in the mantle. Okay, so let me pause, see if there's any questions. Okay. So this is one of the two things I mentioned of these Fuchs, Hamkins, Reitz results. This is forcing a model where V equals the mantle. On the other hand, the other thing they said we can do is that we can force the ground model to be the mantle of this class forcing extension. So let's talk about how to do that. So a similar sort of idea. So we want to code all of V into the mantle of its extension, but we don't want to code anything else into the mantle. So how do we do this? Well, it's a nice idea. We're going to take the same idea, but instead of doing an iteration of these generically making GCH hold or fail, we're just going to do a product of making it hold or fail. So same idea as before, but we do a product instead of an iteration. Okay, and so we have to show two things now. So first is that if you take a set in V, then it's in the mantle of the extension. And this is just the same density argument. The point is everything in V is going to get coded by density into this product. Okay. Because, you go out far enough and, you're just like then like the 0-1 pattern of whether you made GCH hold or fail, that's going to code X. Okay, and the other thing we want to show is that if you're not in the ground model, you're not in the mantle. Okay, so if you're not in the ground model, you're not in the mantle. And so the idea here is we're dealing with a product. Products you can split and then swap the order of the two coordinates, unlike iterations. So we can split our product, this class length product, into a set size forcing P head and a sufficiently closed tail. So since the tail is so closed, we can't have added X by the tail. But then we had to add X by the head part. But the forcing by the tail is a ground of the extension because it misses the extension by a set forcing, namely forcing with this set sized P head. So we found a ground which doesn't have X, so X doesn't get into the mantle. So that shows that V is exactly the mantle of the extension. So we think these are a nice pair of arguments. It's neat that it's just iteration versus product, gives you the two extremes for what you code into the mantle. Okay. So I want to pause for a minute on this slide because this forcing is going to form the basis for a lot of what comes later. Okay. So that's kind of the warm-up, just talking about the mantles. Let me get to what I think is the main topic of this talk, which is inner mantles. So, we saw that you can force something to be the mantle of the extension. You could repeat that process, do it again, and you could keep doing this. So you could get a model where you take the mantle that's not a ground, you take the mantle of the mantle that's some even thinner in a model, and you can keep doing this over and over and over. And you might as well, kind of with the same theme of geology, of looking at things from the downward perspective, you might as well just start with a model, look at the mantle of the mantle, the mantle of the mantle, the mantle, and so on transfinitely. And then you can ask, are these different? Okay, so definition, let's give it. So the sequence of inner mantles, M eta for eta and ordinal, you define it recursively. You start with V, successor step, you just take the mantle of that inner model. And at limit steps, you do the only reasonable thing, which is take intersections. Okay. And so this gives you a sequence. Possibly at some point it stabilizes. For example, if you start off with a model of V equals L, then all of the inner mantles will just be L itself. That's not very interesting. But you can ask, maybe it's longer before it stabilizes. How long can we get? Is every model the eta inner mantle of some extension? Okay. Yeah, so this is what I just said. So this was asked in the Fuchs, Hamkins, Reitz paper. Is there a class forcing notion which forces the ground model to be the eta-th inner mantle of the extension? And I didn't write it on the slide, but of course we want this to happen non-trivially. Because of course, if, like this L example, L is its own eta-th inner mantle, so just do trivial forcing, and it's the eta-th inner mantle of the extension. So we want this to happen where all of these things below the eta stage are different.
Kameryn, I have a question.
Go ahead.
Aren't you pulling a fast one, though? I mean, about the definability of it.
I will address that in a moment.
Okay, good.
Yes, I am sweeping that under the rug right now. Okay. So Joel anticipated the next question, which is also from his paper with Gunther and Jonas, which is, what happens at limit stages? The mantle is definable. And so that means the second inner mantle, the third inner mantle, and so on for all standard n is going to be definable. But why should the limit stage be definable? Maybe, these definitions are getting increasingly complex because you're relativizing this thing and you're relativizing relative to that. So why can we find a uniform way to express them? So is it consistent that, say, m omega is not a definable class. And you can also ask, is it a definable class but doesn't satisfy AC? So we know the mantle satisfies AC. This intersection thing guarantees ZF, but it doesn't by itself guarantee AC. Okay. If these questions look a bit weird, let me point out that these were asked about the sequence of iterated HOD and answered for those by Mikaloon, Yak, and Zadrojny. All did important things, as did Harrington. I think I have the precise citations later. So it's basically just looking at the HOD case and asking, does that happen with the inner mantles? Okay, so I guess spoilers, I will talk about all three of these questions by the end of this talk. Okay, yeah, so yeah, I guess I did include the slide. So iterated HOD, you can do the same thing for HOD where you take HOD of HOD, HOD of HOD, and so on. You get that every model is the eta-th HOD of some class forcing extension, and then you get the two negative results. Consistently, you can have a definable limit stage which doesn't satisfy choice, and consistently the limit stage is not a definable class. Okay, so let's talk about what I call the positive results. So this is the part that's joint with the Jonas-Reitz.
Can I ask another question?
Yes.
So is it consistent, say, in an omega non-standard model that some finite HOD n doesn't exist? Because we don't have a uniform definition of HOD alpha, even for finite ones. There's not a uniform definition, right? Isn't that the point?
Right, yeah.
So can you have an omega non-standard model so that even some non-standard, for some non-standard n, finite n, HOD n doesn't exist even? Is that possible? Does it follow from the Harrington argument?
Yeah, so it's going to follow from the Harrington result. So really briefly, the point is Harrington gives you an extension which can, so its omega HOD can define the satisfaction predicate for L. And so if you then take a model, say, which doesn't have like a satisfaction class for non-standard n, then the Harrington result is going to give you that you can't go far enough out for that. I think I didn't say something wrong. I don't want to say that with 100% surety, but I think it does answer your question. Okay, so let's talk about how to build models, or how to build a forcing extension so that the model we started with is the eta-th inner mantle. Okay, so here's the theorem I have with Jonas. So there's a class forcing notion. Let's call it blackboard bold M of eta, M for mantle. And it's uniformly definable as parameter eta. And forcing with this makes it so the ground model is the eta-th inner mantle of the extension, and this happens in a non-trivial way. I tell you, before eta, all of these inner mantles are different. Okay. So let's take the next several slides to talk about why this is true. So, here's kind of the idea behind the proof. If eta is finite, I guess I mean standard finite, don't interrupt me to ask that, Joel, it's pretty easy. You just do the Hamkins Reitz forcing eta many times, and then you just kind of unwrap it backwards. So you do this eta iterated extension, and so what's the first mantle is you strip off the last generic, because to get to this full forcing, you're just forced with this thing that makes the ground model the mantle the extension. When you take the mantle of that, you strip off the next last thing. And each time you take the mantle, you strip off the last generic. So if you do it eta many times, you get all the way back down to where you started. There's a problem here, though, if you want to go beyond finite, which is that the order that we're stripping these off is the reverse of the order of the iteration. So, the first step was to strip off not the first thing, but the last thing. And so this means if we want to do this for infinite eta, we don't want to do an eta iteration. We want to do an eta star iteration, where you just flip eta backwards to this anti-well order. Okay, so iterations on ill-founded orders, that's a really hard problem in general. We don't have a general theory of this, and possibly we can't have a general theory. But it does turn out we can handle this special case. And so that's the idea then, is we want to do this Fuchs, Hamkins, Reitz partial order. We want to do an eta star iteration of that. If we can figure out how to do an eta star iteration of the Fuchs, Hamkins, Reitz partial order, that will give us the result. We'll just basically do it eta many times because we'll just peel it off starting from going backwards with this eta star. Okay. And so let me give you kind of a picture defining the forcing. So let's fix our coding region. It's appropriately defined, so it's spaced out, will be definable with the extension, et cetera, et cetera. That's not the interesting part. And so it's going to look a lot just like how you would do a normal iteration like we did back in the forcing v equals m in the extension. So what does the condition look like? The domain is the initial segment of R. At a coordinate alpha in the domain, what is P of alpha? Well, it's going to be this lottery sum where you either make GCH hold or fail at alpha. Okay, so right now this is not really saying much. This looks like either the product or the iteration we saw before. Oh, how do you extend? You also extend in the obvious way. You can make the domain larger and you can extend at each coordinate.
Could you clarify the coding region? This is for one step in your ill-founded iteration, or is that what you're
I will clarify immediately. Actually, that's the next thing to say.
Okay.
Yeah. So, you know, we have to say more to get something that's different from this product or iteration, normal iteration we saw before. So what are we going to do is we're going to take this coding region and we're going to split it into a bunch of congruence classes. So what do I mean by that? I mean, you're just like, you know, if you have like, say if eta was 2, you would do every other thing in R for the 2 classes. If eta is omega, you split into like the omega iteration, the omega congruence classes. And the idea is we're going to use these congruence classes for the eta many steps we want to do. So if we look at the bits of R with index greater than I and let I increase, that's going to form a descending sequence of order type eta. And then for a given alpha in R, let I of alpha just tell you which one of these congruence classes you're in. That's the index of alpha. And so what are we going to do? So P of alpha is going to be a named and appropriate intermediate extension. What extension is, okay, so we're going to look at things below alpha, but we're also only going to look at things with larger index. So instead of taking everything below alpha in order to look at the where we're defining the name, we're only taking the things below alpha of higher index. So that's what makes this different from this just ordinary iteration, which gives you v equals mantle of the extension, is we're severely cutting down this like iter model we're defining things in. Okay. And yeah, and so how do you then like define the order? Is it, you know, P over the appropriate extension forces that you go lower. So it's this kind of weird iteration where you're not taking the full intermediate thing, you're taking an inner model of the intermediate thing. Okay. So it's a bit complicated, the definition. So I gave it again all in words on the next slide. So again, so kind of the idea is we're going to let these like parts of the region with index greater than I, those are the things that are given to give us this eta star iteration. And so what is them eta? You know, conditions are set size functions, is domains and initial segment. P of alpha is restricted to the things with bigger index below alpha name for a condition to generically make GCH hold or fail at alpha. And then you get stronger if you extend the domain, or it's forced over the appropriate extension that you're stronger.
Sorry, can I just ask a question?
Yeah, go ahead.
Just to make sure I understand this, is part of the intuition here that the coding region was really unimportant? So if you just kind of cut it up into pieces and you have a smaller coding region, it really doesn't make a difference as far as the one step goes?
Yeah, exactly. That's exactly the point. Yeah. So the coding region doesn't matter as long as you can still recover it in the extension. So if R was sufficiently absolutely definable, then it's also absolutely definable to say, okay, just take every omega thing in R. That's still going to be a good enough coding region. You could use that instead.
Okay, great. Yeah. Thank you.
So great question that highlights something I meant to say and forgot to say. The coding region does not matter beyond being sufficiently absolutely definable. And that's why we can freely change it around.
Can I ask, what you're calling them congruence classes? Is there, I missed the congruence.
Oh,
is it just simply it's a partition?
Yeah, it's a partition. So I'm just thinking like R sub I is, the eta of, if you like do division mod eta, if that makes sense. It's the I remainder
Okay.
I.
Right.
So
Yeah.
it's
No,
like
the last
eta
one-
times I plus I.
Thanks. That's all.
And I'm sorry, can I ask a question also? So the coding region is a proper class, or?
Yes.
Okay. So it's the ordinals at which you're doing the GCH coding for the
Yes.
purpose of that index of the overall system of models that you're trying to create. Is that a
Right, exactly. Yeah. So yeah, I guess maybe so if we start with the ground model that satisfies GCH, your R can just be like the regular cardinals. It's just if you don't satisfy GCH, you have to space it out a bit, because if you're destroying, like forcing GCH to hold at a point, you're going to destroy some information. So you want to space it out based on like the strong limits. Okay, later on, we're going to need this forcing to be eta plus closed, but that can be arranged by just restricting the coding region to be above eta plus. So I should mention that now. We're just going to assume R doesn't contain things below eta plus, then we're going to get sufficient closure. I guess I should say this weird iteration is set support. Okay, so there's a lot of questions to ask. So this weird iteration of order type ord is how we defined it, but I said it's supposed to be an iteration of order type eta star. So I still have to tell you how to do that. Kind of maybe even more basically is, can we say something about closure and distributivity conditions that are satisfied by this? And does this even preserve ZFC? Is, maybe not so obvious at this point. Okay.
Sorry, one more question. Is it, I mean, you're calling it an iteration, but is it clear that it's an iteration, not a product? I mean, if I go from alpha to alpha plus one stage wasn't in the, I guess I go from alpha plus one to alpha rather, and that wasn't in the extent, I mean, in the ground model or something?
Are you mean talking about as an eta star iteration or an ord iteration?
Either.
Yeah, so the point is, so if alpha is big enough, then, so say like eta is 2. And so say alpha is like the omega thing in R. So if alpha is the omega thing in R, we've had lots of stages below alpha where we did the second thing instead of the first thing. And so we are going to have like these intermediate stages below alpha, picking out, say, like all the even things below it.
I see. Okay, thank you.
Yeah, so we do, it's not a product. It is actually getting new information.
So can we understand it as a sub-forcing of the ord iteration that would be more naturally defined, but you'd pick out the subsets very carefully so that you can view it as an eta star iteration? Is that?
So I'm not sure if suborder is the right word, but we want to take this iteration, and the idea is at each stage we just instead of looking at like defining the iteration in the full intermediate extension, we look at a submodel of that intermediate extension. So that's going to give us.
Condition in your forcing is literally also a condition in the. Full.
Yeah. So it is a suborder then, yeah. So it's a suborder where we pick out at each stage, we just like restrict the like model the names are allowed to come from.
Okay.
So this idea of doing an iteration where at each stage, instead of looking at the full intermediate extension, you look at a like submodel of that. This is what Jonas calls a generalized Cohen iteration. He did some stuff about this. And so using this technology, we can answer these questions. I'm going to sweep the details under the rug because it would take a bit of time to go into it, but let me just briefly tell you what you get. So we get that this is what we call a progressively distributive iteration. What do we mean by that? We mean that for any alpha, you can split it up into a set-sized headpiece and an alpha distributive tail. So it's the small thing iterated with this distributive tail. And in particular, anything like this is going to preserve ZFC. So if you know how to show like progressively closed iterations preserve ZFC, well, all you really use was progressive distributivity to get that. So it's going to be exactly the same argument to show it preserves ZFC. Yeah, and so it's exactly like Joel said. The idea is you think of this as a suborder of the full iteration where you're just restricting where the conditions come from. Okay. And then also using this, you can show that the coding regions, well, as long as R was picked correctly, then it's going to be preserved. And the intermediate things will then be preserved for free because they're absolutely definable from R. And we also get that these restrictions to these intermediate pieces is also going to be distributed iterations, it's going to preserve CFC, going to preserve R, and so on. Okay. So that's good. The forcing preserves CFC, and we can say something about distributivity conditions. I guess maybe let me say something about distributivity here. So with the full iteration, you get this progressively closed iteration. So you get closure, not just distributivity. With these generalized co-iterations, you only get distributivity, not closure. But it's still good enough for our purposes, so that's fine. Okay, but I haven't yet told you in what sense it's an order type, an iteration of order type eta star. So that's what I want to tell you now. Okay, so for notational convenience, let me rename everything because I have lots of subscripts and it's annoying to have indices and subscripts after parentheses. So let's call the whole forcing P, and P sub I is going to be the restriction to coordinates with index at least I. And so if we do this, then we get a descending chain of forcing notions. P0 contains P1, contains and so on, with P eta as the smallest thing. This is a continuous descending chain. And at each stage, we're taking suborders as we go, complete suborders as we go down. And so since these are complete suborders, in particular, this is telling us that we can factor each of these as PI iterated with the remaining things we haven't done yet. And so this is the sense in which it's an eta star iteration, because of course, complete suborders are exactly like the things that are the first term in an iteration. Okay. And so what's our strategy then? So maybe let me say then, so let's say if we take a generic over this forcing, we can do the restriction of the generic to these sub orders PI, we'll call it GI. So in particular, G eta is the trivial filter over the trivial forcing P eta, because if we intersected all of these, what has index greater than or equal to eta? Nothing has index greater than or equal to eta. The indices are less than eta. And so what's the strategy is we want to show that as we step down this partial order, we're going to be stripping off mantles. So if we look at the forcing from the whole thing, we strip off the biggest part of it. We're going to go one step down. That's the mantle. We go another step down. That's the secondary mantle. And we're going to do this transfinitely all the way down to the eta-th stage. So it's like what we wanted to do is this eta star iteration. And so that's the correct order type to get what we want. Okay, and we're going to prove this by induction, of course. The base case, of course, is trivial. And so it's the other cases that need work. So the successor step, I think, is hopefully pretty straightforward. So how does PI factor? So PI plus 1 is a complete suborder of PI. And so how do these differ? Is these differ by the guys that have indices exactly I. And so what happens at index I is we're looking at R sub I, and we're doing this product of generically making GCH hold or fail. That's what's happening at the ith stage of this eta star iteration. And so now the successor step is just the Fuchs Hamkins Reitz argument. We're doing this product, so it's going to give us exactly what we want. Okay. Let me pause to ask for questions. Okay. So we do have to say something about the limit stage, because of course, in general, if you just intersect a bunch of extensions, you know, why do you get the intersection of the extensions is the intersection of like the forcing by the intersection. And so Yek, in the context of proving some of these results about HOD, proved this lemma. So let's suppose you have a continuous descending sequence of limit length. And let's suppose these are complete sub-Boolean algebras, and the top one is sufficiently distributive. And so then Yek's lemma tells us that if you have something that's generic for the big thing, and if you're in the extension by all of the intermediate stages, all the BJs, then you're exactly going to be in the extension by BI. And so this is exactly what we want to do to make the limit stage go through, is we need to say, if you intersect all the intermediate stages, these are the smaller inner mantles by inductive hypothesis. We intersect all of these, then we get exactly the extension by the intersection of all of the Boolean algebras. Okay. So, Yex lemma was proved in the HOD case exactly to make the limit stage go through, and we'd like to do the same thing in the mantle case. There's a bit of a hurdle, though, which is this is talking about complete Boolean algebras. And, with class forcing notions in general don't have Boolean completions. So you can't directly just say, okay, take these class things and find their complete Boolean completions and then just do Yex lemma there. Okay. So the way we got around this restriction is we just noticed that, we could reduce our problem to Yex lemma. So specifically, if we have a progressively distributive iteration where we can factor it with a sufficiently distributive tail, then if we just look at the intersection with the set-sized pieces, these are set forcings. And so this is going to form a chain exactly like in Yex lemma, or rather the Boolean completion of these set-sized pieces. And since this tail is sufficiently distributive, things had to have been added by the set-sized piece. And so this is going to be good enough to get the conclusion of Yex lemma. So how do we show that X is in the intersection of set X? Well, we just split this so that this alpha is large enough that X can't be added by the tail. And we just immediately apply Yex lemma to get X as in the extension by the intersection. Okay. And so let me highlight, this is where we use the assumption that our forcing is eta plus closed. I guess we only needed eta plus distributive because that's what we're using to make Yex lemma work, but it's exactly going to go through. Okay. And so this then gives us the limit stage. We've reduced it to Yex lemma, and now we can go through the limit stage, and we just do this induction up to eta, and then we're done. And so that then completes the argument for the positive case. We have start with the ground model. We do this eta star iteration, and then now you work backwards in order to type eta, and each step as you go along, you're getting a strictly smaller inner mantle until you get back to the original ground model. Okay, so I guess I don't think I put a slide for it, but let me just say verbally an open question. Can we get an ord length sequence going on here? So you can in the HOD case. Zadrozhny improved upon like the Yex methods to get an ord length sequence of descending HODs. But Jonas and I weren't able to figure out how to get his arguments, his machinery to generalize to this context. So we can get an eta-like length sequence of intermantles for any eta. Can we get ord length? That's still open. Can we go beyond ord? That's still open. Because of course, if you have an ord length thing, you have the orth intermantle. You can ask, what's the mantle of the orth intermantle? What's the mantle of that? You can go well beyond ord. Okay. But I want to switch topics now. I want to talk about negative results. So we've seen that you can have positively that lots of intermantles exist as far out as you like. Can we have bad cases happen where the limit stages aren't definable, don't satisfy choice, etc.? Okay. So I think I maybe said this earlier in response to questions, but let's say it again. Let's reorient ourselves. So just an easy observation, if the eta-th intermantle is the definable intermodel, then so is the eta plus first, because you just take the definition and you relativize the mantle of that definition. That's a definition, so it's the definable intermodel. And so the question then is, if we're going to have something undefinable, it's going to have to happen at the limit stage. So if m eta is the definable intermodel for all eta, let's say limit gamma, is m gamma a definable intermodel of ZFC? Okay. And the difficulty is the definitions are increasingly complex. So we're basically asking, why can we find an alternate uniform definition? So
couldn't it happen at a non-standard finite?
Yes.
Also.
Yes, that's also a question.
So it's not a limit ordinal, right?
Right. So there you would get the same sort of thing. So if you had like a non-standard stage E, then the E plus first stage would be definable. So you're asking about a cut then in the omega of the model, which isn't a limit ordinal, but it's kind of like a limit ordinal because there's not a largest one. It's just not actually in the model. Okay. So yeah, as Joel points out, this can happen below limit stages in a non-standard world, but I'm going to focus on the standard world because that's what I have the results for. I think the non-standard thing should follow the corollary, but I don't want to say anything at the moment about that. Okay. And so maybe let me just make an observation. So if you extend your, go to a second order set theory, take classes as actual objects, then a strong enough principle is going to give you that M eta always exists. So specifically, if you allow elementary transfinite recursion, so what does this say? This is if you define a class by transfinite recursion of first order properties, this class exists. So for example, the Tarskian satisfaction class, you define this by recursion of height omega. And so ETR would say that truth predicates exist, for example. But this definition, this is the definition by transfinite recursion. Each step is a first order thing. Either take the mantle, that's a first order thing, or take the intersection of a bunch of things, that's a first order thing. So if we have ETR for long enough recursions, we're going to get M eta for all ordinals eta. It's a definable inner model. And if we take ETR beyond ORD, you can do like transfinite recursion for things of length ORD plus ORD times ORD, and so on. Then we get that we can have meta-ordinal length inner mantles are definable. Again, it's an open question whether these are different. Maybe like once we get to the ORD stage, they're just all the same, but they're definitely a definable inner model no matter what. Okay. And so this kind of suggests that if it's going to be undefinable, it's got to somehow block being able to put ETR on in the classes. Okay. This is kind of a, easy little proposition. So another thing that might go wrong with limit stages is, it's pretty easy to see if you have like a descending sequence of inner models, you have uniform access to it, then the intersection of all these guys is going to satisfy ZF. You can do this like sort of covering type of argument. And so you're going to get everything except possibly the axiom of choice. And so this tells us that there's two things that can go wrong at limit stages with these inner mantles. Could be that it's definable, but it doesn't satisfy the axiom of choice. And it could be that it's undefinable, which is to say that the sequence of things below it must be undefinable. Because of course, if the sequence was definable, you could define the next stage by just taking the intersection of everything in the sequence. If the sequence is definable, their intersection is definable. Okay, and we're going to see that both of these possibilities can happen. I'm going to do it for gamma equals omega. And this basically is an adaptation of the results about these negative results about the omega iterated HOD. Okay, so let's talk about coding sets and inner mantles. So for the positive results, Jonas and I used what let's call continuum coding. So we coded sets of ordinals by the pattern of where GCH holds and fails. If a set of ordinals is like an ordinal sequence of zeros and ones, you just look at, 0 is GCH fails, 1 is GCH holds, and you can just read off the zeros and ones. But of course, there's lots of other ways to read off zeros and ones. So I know Andrew Brooke Taylor has done some interesting work on this with coding with like various kinds of trees and whatnot. For this, I want to use a very simple coding, which I'm going to call co-encoding. And so this is where you just look at which cardinals have subsets which are co-generic over L. And so this is nice because you can code something by adding a single co in set. Whereas with GCH, you're adding like a whole big block of them to make it fail. Of course, this coding is applicable in fewer universes of sets. If your model already has a co-generic over L for every cardinal, then you can't do any coding because you're just going to have this big long sequence of ones and you can't get rid of that. Okay, but that's fine because we're just trying to build counterexample models. So we don't need this to apply everywhere like we wanted to with the positive results. We just want to get some place where this applies. And in all cases, we're going to start over L. And so basically over L, we have a lot of control over when we do forcing, which cardinals have co-generics. Okay. And the reason we do this is just simplify some arguments because it's a little simpler coding. Everything would go through with the more complicated coding. It would just be more work. And so I don't want to do more work, so I'm going to do the simple coding. Okay. So as a warm-up, let's talk about coding a single set into the mantle. So earlier we did this by genericity. We just did this big lottery sum, and the generic then picked where the set of ordinals was coded. But if we're just coding a single set, we can pick where to code it and say it a bit more precisely. Okay, so I guess first of all, lemma that's analogous to the lemma about continuum coding. Grounds agree with V on a tail about which cardinals contain Cohen generics over L. Set forcing can't add a proper class of Cohen generics over a model of choice. Okay. And so how do we do this is you're just gonna, do the obvious thing. You have a block where you're doing the coding, and you're gonna add a new Cohen generic exactly where you want a 1, and you don't add it where you have a 0. So for convenience, let's assume that our set of ordinals doesn't contain its supremum. That just makes this a little easier to say. Of course, you can do this without loss of generality. And so let's suppose we have a appropriate coding region. It's going to be sufficiently absolutely definable, and we don't have any Cohen subsets on the region. So it basically starts off, the region is all zeros, and we're just going to add the right pattern of 1s. How do we add the right pattern of 1s for this region of zeros? We just force the product, where we add a single Cohen real where we have a bit 1. And we want to do this cofinally often. So we don't just want to do it, code it once. We want to code it again, code it again, code it again, and so on, ord many times. So you can think of it, we break R into blocks which have length lambda. And then in each lambda block, you just look at the ith coordinate where I is an x and add a Cohen subset there. And so the point is, on these blocks in R, where you look at lambda many things in a row, then you're going to have a 0, 1 pattern that exactly tells you x. Of course, if you're just coding things in a HOD, you only need to code once. Because it's the mantle, though, we need to do this cofinal often coding. But the idea basically is just, x is a sequence of 0s and 1s. We just make these 0s and 1s sequences over and over and over. Okay. Of course, we want to code into more than just the first mantle. We want to go even deeper. So if we can do it once, can we go even deeper? And yeah, so if we want to do this, we're going to have to do what I'm going to call tree-like coding, because it's built like a tree. So again, the idea is we're going to break our region into a bunch of sub-regions. So I'm calling these R sub S, and let's break it up, say, by finite sequences of ordinals. And we're going to start with R of the empty sequence. And we have our set X, which we want to code. So what do we do is you just repeatedly code it like we said on the previous slide. We get the 0, 1 pattern, same 0, 1 pattern. We do this cofinally often. And so these blocks of the generic, we can think of these as sets of ordinals. We have the first block, the second block, the third block, and so on. By using a pairing function, these are just sets of ordinals. And so what we're going to do is we're going to code each of these sets of ordinals cofinally often. So let's do it. We have to now, because we have ord many of these things, we have to have ord many coding regions, but we split up R to have enough coding regions. And so we're going to code this first guy cofinally often. We're going to code the second guy cofinally often. We'll code the third guy cofinally often, and so on. And then we just keep going. We have this level of the tree, everything here, we code ord often. We have, ord many little spots to code, so that's fine. And if we want to get into the kth mantle, then we want to do this for all sequences of length less than k. So the idea basically is, we do it once ord many times. We have to do each of those ord many times, each of those ord many times. And so we get this tree that looks like less than k ord. So the full ord branching tree of height k. Okay, and you can arrange things because these separate codings are independent. They're just products. So you can think of this as a k-step iteration of class products. So I'm going to call it k-height tree-like coding, and we can tag it with the height, the region, and the set we're coding. Okay. Questions about this coding forcing before I talk about its properties? Okay. So digging deeper through inner mantles corresponds to climbing down the tree. So after forcing with this, cutting off the generics on the top layer of the tree, that's digging down 1 mantle. And this is because at each stage we did these products, and this product forcing makes the extensions mantle be the ground model. So if you're at like the top and you take the mantle, you cut off the products to cut off the top level. But everything below that is still going to be in the mantle because it was sufficiently coded. And so if you take another inner mantle, you climb down the tree, climb down again, and if you do it k times, you get all the way down to the bottom. So this is just basically the Fuchs, Hamkins, Reitz argument over and over. Also, we can do this coding separately on disjoint blocks, and they're not going to interfere with each other. So we can take like a product of these t's, and we're going to code x in one region, we're going to code y in one region, and we can do this with independent heights. And okay, maybe you have to sweat a bit, not sweat, it's maybe a little tedious to check, but this is uniformly definable in the parameters. So if you have a uniform listing of your k's, your regions, your sets, your coding, then you can define the product of all of these. And so you can code like infinitely many things separately. Okay. And so using these tree-like codings, we can adopt Michelun's proof in the HOD case to get it for the omega-th mantle. So specifically, let's see that there's a class forcing extension of L in which the omega-th inner mantle is a definable inner model which doesn't satisfy choice. Specifically, there's no well order of the power set of omega in this M omega. It should say in the M omega of this extension, not the extension. Of course, the extension is going to satisfy full choice. Okay. So yeah, so this is following Michelun's argument for HOD omega. We just have to do a more complicated coding for the mantle instead of HOD. So what's the idea? We start with L, and the first thing we're going to do is we're going to add omega-1 mini Cohen reals. And so let's think of this as a big binary grid. We have, I guess maybe I'm thinking of this sideways from how you might think of it. I'm thinking of omega-1 many rows. These are the Cohen reals. Each row is a Cohen real, and each column then is a like the 0th bit, the first bit, and so on. Okay. And so let's say that AK is this block from the kth column onward. So what is like A sub 1 is we just cut off the first bit of each Cohen real. What is A sub 7 is we cut off the first 7 bits of each Cohen real. So of course, cutting off finitely many bits from a Cohen real, that's still a Cohen real, just a smaller one. And so we're just basically, these AKs, we're just like sharing off more and more of these Cohen reals. Okay. Notice each of these AKs is a, basically omega-1 many Cohen reals. Okay. And so let's take disjoint coding regions, which, I'm going to sweep under the rug how you define it. It's kind of easy. And okay, we don't want to add new subsets to omega-1, so let's not let omega-1 be in the coding region. And then we're going to basically code AK in the kth coding region to be into the kth inner mantle. Okay. So, right. So what's the idea? You cut off the first, say, 17 bits of each Cohen real. That gives you these omega-1 many Cohen reals. And you code this into the kth inner mantle. And so, as you get farther and farther along, you're cutting off more and more of these bits. And so let's call the extension LAG. Okay, and then we want to kind of build downward. And so with these tree forcings, we said climbing down the tree is going through inner mantles. And so let's define the G to be that same way. So GK is the portion of generic corresponding to sequences at least K many levels from the top. So G0 is everything. G1 is cut off the top levels, G2 is cut off the next level, G3 cuts off the next, and so on. So notice, for example, that since some of these we only coded, K might be small, say K equals 1, then eventually GL for large enough L is just going to get rid of that whole tree. But we have omega many trees, so we're still always going to have something. And then you can inductively show, similar to the positive case argument, that this climbing down these omega many trees is corresponding to digging deeper into the mantles. Okay. So easy observation, each row of A comes from an AK by just putting these finitely many bits back. So, if you have this infinite binary sequence, this Cohen generic, and you have 0, 1, 0 as what you cut off, well, you can put 0, 1, 0 back on, so that's going to be in your model. So each row is going to be in the omega inner mantle because each row is recoverable from each AK. You're just not going to have the whole block of A by itself. But each individual row Okay, yeah, each row, I'm not being inconsistent. Each Cohen real is in the omega theta mantle. And because we didn't change anything small, we have the same omega 1. Okay. And so this tells us then, so if we have a well order of a power set of omega, it's got to have one of order type omega 1. Because, you know, and the extension is we didn't blow up the power set of omega to be larger. And this is going to happen if and only if there's some subset of omega 1 which constructs the whole power set. Because, you know, basically, if all of these are constructible from it, then we look at the well order in here, that's going to be a well order of all of the power set of omega of the omega theta mantle. And so we just have to show there's no such X. So you can't have a single subset of omega 1 that tells you all the reals in the omega theta mantle. Okay, this isn't so bad. So because the forcing to add all these like tree coding things didn't add subsets to omega 1, if we have an X like this, it had to have been added by this intermediate forcing immediately. So this was the forcing where we added omega 1 many Cohen reals. Okay, so we added a set by add omega 1. We added a set by a CCC forcing. So that means we could have added it by a countable piece of the CCC forcing. What's a countable piece of the CCC forcing? It's a countable selection of the rows. So we just go up to a countable height, throw away everything above. That was good enough to get the subset of omega 1. Okay, but now by mutual genericity, if you took a row that you threw out, then you couldn't possibly get it from this X. But this then shows we have a real in M omega, which wasn't constructible from X. That's what we wanted to show. Okay. And so that would complete the argument. That shows that the omega theta mantle lacks a well order of power set omega. So in particular, AC fails. Oh, I didn't say why it's definable. It's definable because in the forcing extension, just say, look, intersect all these things. That's the definable thing to say. We had a uniform access to the mantles because they came from this sequence of generics. Questions about this before we see the other negative result? Okay. So this is going to follow Harrington's argument for HOD omega. So Harrington showed consistently HOD omega is not a definable class. How did he show this? He showed you could have a HOD omega that could define the satisfaction predicate for L. And if you have that, then you're going to get models whose HOD omega is not definable. So same idea. We have a class forcing extension of L in which the satisfaction predicate for L is definable over the M omega of that model. And so as a corollary, we get some that are not definable. So let's see how to get the corollary from the theorem first. So let's say that a model of ZF is a Paris model if all of its ordinals are definable without parameters. Okay. So the minimum transitive model is a Paris model because it's pointwise definable. If everything's definable with parameters, so is every ordinal. But, you know, we can get a lot more Paris models. So Paris, hence the name, showed that every consistent completion of ZF has a Paris model. So there's lots of them. Necessarily, these all have countable height. And so let's also notice that if you have a model of V equals L, that's a Paris model, then all of its outer models also have to be Paris models. Why? Because you just relativize to L, you define all the ordinals there, but that gives you a definition of the outer model. And the other thing let's notice is that if you could define the satisfaction predicate for L, then that's going to give you a surjection from omega onto org, because you just take the K formula and you map it to the ordinal defined by that K formula. You can do this mapping because the satisfaction predicate is definable. So if your outer model can define the satisfaction predicate for L, then you're going to be able to get this bad failure of replacement, so it couldn't be a definable class. And so this is exactly the strategy then to get models whose omega inner mantle is not a definable class. We're going to start with the Paris model and get this outer model that can omega mantle can define the satisfaction predicate. Okay. Yeah, so if you have an extension of a Paris model that equals L, omega mantle can define the satisfaction predicate for L, can't be a definable class in this case. All right. So that's the strategy. And so the idea to prove this, as I said, goes back to Hamkins' argument for HOD. And so the point is we can define to each formula phi with parameters from L a cardinal, and we want to code things so that we have a Cohen subset of this cardinal if and only if phi is true in L. And so how are we going to define the satisfaction predicate for L is given a formula with parameters phi. You look at kappa of phi, you ask, does kappa of phi have a set which is generic over L, Cohen generic over L? Yes says this is true, no says this is false. Of course, though, we want the forcing to be definable. You can't just say, look, let's start with, just add the Cohen subsets just on these points, because that's a forcing that uses the satisfaction predicate to define it. So we want to be more clever, and by we, I mean Harrington, and we want to define this coding forcing using only a bounded level of truth in L. If we can do this, then the forcing is definable. Because, we have a definable truth predicate for like sigma 1 truth. Sigma 2 or whatever. So that's the idea. Okay, so I'm going to need more coding tools. So let's talk about those. So we did tree-like coding earlier of finite height. You could keep going to omega height. Just build the full tree up omega high. And if you do this, then there's no top to the tree. So if you try to dig down to the inner mantles, it's not like there's a top level that isn't coded. You take any level in the tree, every generic there was coded the next level up. So if you take a mantle, you're going to have the whole tree is still, everything in it is coded. So if you do this, every piece of the generic is going to be in the first mantle, the second mantle, and so on. And so this is a way to guarantee that something gets into the omega inner mantle, because it's just going to be in everything. Okay. Also notice you can do these tree-like codings for proper classes, not just sets. You can, how did we code the first level of the tree? We broke it into set-sized pieces and coded all of those. So if you have a proper class X, break it into set-sized chunks, code all these chunks independently on subregions. You can split all these things up in a definable way. It's ugly to write down, but I hope it's clear how to do it. Okay. And then kind of the key idea that lets all this work is you can destroy coding information. So how do you destroy coding information? If you think like a hard drive, just overwrite it with all ones. What we're going to do is we're going to take our region R, we're just going to add Cohen generics everywhere, make the 1, 1, 1, 1, 1, 1, 1 on that region, and destroy all the information that was coded there. So let's call the forcing, which just adds Cohen generics everywhere, the overwrite forcing O. So we have omega tree-like coding to force you to be in all the inner mantles. We can do this for a proper class, and we can also overwrite things. And all these things you can do on different coding regions. They don't interfere, take a big product. These things are uniformly definable in the parameters, et cetera, et cetera. Okay, so let's see a toy example before we see the real example. So what is this forcing? We have a Cohen generic X we want to code somewhere. So first we're going to do omega height coding on X. We're going to get some Y, set of ordinals, and we're going to do two things. We're going to code Y with 7 height coding. That will force Y to be in the 7th inner mantle, but we're also going to overwrite the region where we coded Y. And then we're going to take this overwrite generic, and we're going to code that using 7 height coding. And so let's analyze what happens in the extension where we did all of this. We coded X really high, we overwrote this code, we coded those things, and so on. Okay. So this code W ensures the overwrite code is in the 7th inner mantle, because that's exactly what 7 height tree-like coding does. It gets you in the 7th inner mantle. So before we get to M7, we're always going to have this region overwritten. But nonetheless, we still have this code Y is definable. We can't define it by just looking at the region and looking at the patterns of zeros and ones, but we can define it by looking at this code Z. We look at Z, Z codes this class, this ord length sequence of zeros and ones. It's on a region that was overwritten, but we can look at Z to figure out what we masked with this overwrite coding. And so this tells us Y is in the 7th inner mantle. And since Y is coding X very strongly, X is in the 8th inner mantle. However, once we're in M7, we no longer can define Y because we don't have this code anymore and we overwrote the region, so we can't just look at the region where we did this coding. So that means that in M8, the 8th intermantle, we're no longer coding X, and so X gets out of the 9th intermantle. So what did we do? We coded X into the 8th intermantle, but not in the 9th intermantle. And I think a reasonable question is, why do this more complicated thing? We already have a way to put it in the 8th intermantle and not the 9th intermantle. Just use 8 height tree-like coding. And the point is that this O was a single thing we could control. If we had gotten rid of the O, X would have survived to the omega intermantle, because we have this Y that would let it get all the way there. And so if we have a way to turn on or off these O's, control whether we overwrite or don't overwrite, that gives us the control for whether or not we're getting all the way to the omega intermantle. So you could imagine if we had in turn overwritten this, then we would have gotten X into the omega intermantle. And we could have overwritten the overwrite and so on. And so this is kind of the idea for how to code things into the omega intermantle that we want, is we want to selectively do overwrites and non-overwrites.
Kameryn, could you clarify, to overwrite means to say add more Cohen sets at each stage so as to push the GCH to fail mode at everything in the region? Is that what overwrite?
So I'm doing this simpler coding where it's just whether or not you have a Cohen generic over L.
Oh, okay.
So overriding is just adding a Cohen generic.
Okay, you're just sort of.
You could do it with the GCH coding the way you
one already.
Yeah.
Okay.
Yeah. So if you think of the coding like abstract, whether you do like Cohen generics or GCH pattern or what, you just have a sequence of zeros and ones like coded on this interval. We're just writing all ones on the interval. I mean, I think of it as like a very complicated hard drive. Like, you know, maybe it's like magnetic, whatever, like high or low, but whatever it is, you think of it as zeros and ones. Okay. And so let's talk about the general method of doing this. Okay. So I'm going to do it for a sigma 3 formula because that was as big as I could fit the picture on a slide. And so the idea is we're just going to iterate this kind of toy example from before. So let's take a formula phi. We can write it as there's an x so that there's not a y, so that there's a z, so that c of x, y, z. C is supposed to be no quantifiers, and I'm suppressing any parameters from L. Okay, and we added a Cohen generic to the cardinal corresponding to this formula phi. And we want to ensure that this Cohen generic is in the omega intermantle if and only if phi is actually true in L. So how do we make it so this C sub phi survives only if phi is actually true in L? Well, we're going to do this omega height coding, and we're going to get a code. So if this code for the omega height coding survives, we got C sub phi into the omega intermantle. And so what are we going to do? Is we're going to do length 2 coding. 2 is 1 smaller than 3 to code this piece. And we're going to do this coding not once. We're going to do this coding once for every possible x in L. So first stage is we already have recoded this proper class ORD many times. Okay, and we also overwrite each of these ORD many times. And so now what are we going to do? So for each x, now we're going to look at each y. And for each y, we're going to take this overwrite coding for that x, and that we're going to do the same coding it, now with height 1. And now we take this, we go 1 higher, and we also overwrite it. So we've done this ORD many times, and for each of those, we do this more coding and overwriting ORD many times. And then we're going to keep going. So now we're going to look at each z. And okay, at this point, we've got to the bottom, or top, I guess, as I wrote it. So for each z, we're going to overwrite, sorry, not overwrite, we're going to code the overwrite block only if L actually thinks this is true. So if L thinks this is true, we're going to code the overwrite block. If L thinks it's false, we're not going to code the overwrite block. So notice this only uses delta 0 truth in L, because C is delta 0, no quantifiers. I mean, no unbounded quantifiers. Okay. And so let's make some observations. So if we have this like triangle coding, taking mantles, you know, ignoring whether like what the overwrite blocks do, taking mantles is just climbing down these trees. So if we take 2 intermantles, we're going to get this back because this had height 2. If we take 1 intermantle, we're still going to have this code here for every y. So this pink code is in the second inner mantle for all x. This purple code is in the first inner mantle for all y and all x. That's just for free. Okay, and so if you fix an x, if one of these guys, one of these pink codes survives, then C phi is going to be in the omega inner mantle. Okay, but in the second inner mantle, this thing gets overwritten if this overwrite block survived. So we have to ask, did the overwrite block survive to the second inner mantle? Well, that means we have to look what happened for y. So this overwrite block for a fixed x, this is going to survive if and only if for some y, y's purple coding block is not overwritten. Because if for some y this survived, then we can recover this whole thing and the whole thing was overwritten. Okay, so when was this overwritten? Well, this is overwritten if and only if this coding block was in the first inner mantle. When is this coding block in the first inner mantle? Well, if this existed for some z. So in other words, this guy got overwritten if and only if there was some z, so that L thinks C of x, y, z. So putting this all together, C phi gets an M omega if there exists an x, so that there's not a y, so that this got overwritten. So there's exists an x, so that there's not a y, so that there's exists a z, so that this holds. So exist, not exist, exist. We're exactly coding it when this is true. So the point is these coding blocks are basically giving you the negations of things. The overwrite blocks give you the negations, the coding gives you the existence. So you just flip back and forth by these negations as you go down. And at the end of the day, you got everything down to just delta zero truth, because if you wanted to, at a certain point, ask what's true in L, well, there's no unbounded quantifiers to ask about. Okay, so this is the sigma 3 case. How do you do the sigma 4 case? Well, you're going to have 4 columns, and you're just going to move everything up by one more step. How do you do the 7 case? You're going to have 7 columns. You're going to need an even bigger triangle. And this then works. You can do this. It's uniformly definable. There's a whole lot of annoying coding going on. You got to split regions into smaller regions, but you can do all that in a definable way. And so you get this whole forcing is definable just from this delta zero satisfaction predicate for L. Okay. I'm going to pause and ask if there's any questions. This is kind of the end of the technical part of the talk. I should say this triangle coding, this is Harrington's idea. My contribution is just doing the coding that works for the mantle instead of HOD. If you do a HOD type coding instead of a mantle coding, that's Harrington's argument. Okay. The question is, so this is just for the omega thinner mantle. What about other limit stages? I don't know yet. My conjecture is you can do a similar thing, maybe like interleave this like forcing to make the mantle long, this positive result forcing, but there's work to be done to answer this. But I don't think omega should be special here. I think you should be able to do it for other limit ordinals as well. Okay. Thank you once again for attending. And here are some references. I guess I should say the positive results, that's published, that's in this paper with Jonas. The negative results, I'm in the process of writing up. The pandemic kind of delayed the writing that up, but we'll get out eventually.
Well, thank you very much, Kameryn. Let's all give him a hand. And now to handle questions, if you have a question, then just type in the chat that you have a question. Just type the word question, and I'll try to organize it that way. So Corey has a question. Corey Switzer.
This was great. Thank you. My question is basically going back to the omega-th mantle that's not a model of choice. Do you know if you can kind of control that at all, in the sense that, like, if you have your favorite model where choice fails, say, the symmetric extension by a Cohen real, can you make that the omega-th mantle or something like this?
That is a fantastic question. I do not know the answer to.
My guess would be that you have to assume some SVC or something like this. Obviously, the Bristol model is not going to be the omega mantle of anything.
Right.
The Bristol model, though, it's kind of, I mean, it's some sort of ORD inner mantle of something, right? Because you're kind of going down ORD steps.
I don't know if I would call it that way.
All right, are there other questions? Now, I have a question, Kameryn. So when you were talking about handling these meta-ordinals above ORD and the ORD iteration and so on, and you weren't sure, I was wondering whether you could just modify your argument. So when you organize that ORD iteration as an eta star and think of it really as an eta star iteration, then couldn't you in principle do the same thing with a sort of gamma star iteration? In other words, fix a meta-ordinal gamma, capital gamma, bigger than ORD possibly. And that's an order type of some relation on ORD, but then do the same thing with the stages I, the stage is bigger than some I, but with respect to that relation instead of with respect to the usual ORD relation.
Right. So this is what we would like, is just do a gamma star iteration. And the sticking point is we needed this extra like distributivity condition to make the limit stage go through. If you're going beyond ORD,
okay,
how do you have something that's ORD plus distributive? You can't.
Right.
And so, maybe you can tweak this to get ORD itself, because the stages below only have to be set distributive for some big set. But it seems it's not going to go beyond ORD.
Okay. Right. Any other questions? So I have another question. So this Harrington argument, I mean, should we think of it as something like a priority argument? It seems very similar, but you didn't sort of present it as a priority argument, like in computability theory, where you're constructing Turing degrees and so on. It's like a zero triple jump argument or something. Is that a helpful perspective to understand what's going on here, or no?
So I guess what I will say is what I know about the argument is to my knowledge, Harrington never published it himself. Zadrozhny wrote a great paper saying a lot of things about iterated HOD, and he presents Harrington's proof in that. And so I learned of Harrington's proof through Zadrozhny's paper. Zadrozhny doesn't talk about it as a priority argument at all. Now, given that Harrington came up with it, very well could have been, that's how he was thinking about it. But that's sufficiently far from my wheelhouse that I wouldn't be able to say whether it's a very good perspective.
Okay. So I have another question.
I think there also might have been some hands up from people I saw.
Oh, I didn't see any hands. There's no questions in the chat, and I don't see any hands.
Oh, sorry, I didn't put my hand up properly.
Oh, okay. Go ahead, Philip.
I mean, I did that wrong. Sorry. So about the earlier argument, I mean, thank you. That was really nice. It looks really smart.
Thank you.
I really like this talk. So in the earlier part of the argument, what kind of...
Can you say earlier where?
Sorry?
Like you're saying earlier, but where do you mean
for the earlier part of your talk, not getting the M omega is not a
like
model.
the positive results part?
Yeah, at the very beginning, right? When you were first introducing the kind of the descending sequence of partial orders, right? This kind of reverse iteration. So what kind of class chain condition are you getting on these PIs or on the QIs, right here? I mean, the regions are proper classes, right? These,
right, yeah.
So what kind of, I mean, is this forcing, has this got some kind of ON chain condition? Is this a set chain condition going on here, or?
I think you're not going to have any nice chain condition because, each stage of this is a ORD length product.
Right.
And so, you're not going to be able to just like have a set sized anti-chain that covers the whole thing.
Right. So you could
say, none of these are going to have the ORD CC.
Right. So it might have sort of like ORD plus CC in some sense.
Yeah, but everything has ord plus CC.
Right, I'm just thinking how to formulate this as this kind of KM argument or something.
Yeah, so I guess in our paper, we did this in Girdle-Bernays just because it was convenient to use that. So you don't need like KM, like the full strength of KM to do this.
Right,
Or you could just do it as definable classes if you want to do it that way.
right, right. Okay, thank you.
So are there any other questions? Well, in that case, thank Kameryn again for an excellent talk, really fantastic talk. And this is the final talk for the Bristol Oxford Set Theory Seminar this term. We'll start again next term. And maybe Philip, you want to say something about the schedule, when it will be?
I don't actually have dates. It will be the same times and on Wednesdays. And it'll be a subset of the Wednesdays in the Oxford term. So we've got some nice people lined up. Not all the slots are yet taken, but we haven't actually organized with them who's actually going to be first.
Okay, great. Well, I hope to see everyone back next term, and please have a lovely vacation. So thank you very much, and see you next time.
Okay. Bye.
Hi, everyone.
Bye.
Thanks for
Thank you.
coming, and thanks once again for the
Thanks,
invitation.
everyone. Bye.
Thank you.